Okay, well, welcome back. This is the second week of our little videos looking at entropy. So this covers the last half of the pack. At the end of the first week's videos, we were able to calculate delta S surroundings, delta S system, and put the two together to make delta S total. And we said that if delta S total was positive, then we said the reaction was feasible. In this section of the notes, we're going to look more at what that means in terms of feasibility. We're going to do some more calculations, and we're going to have a look at why sometimes those reactions might appear not to have occurred, even though the delta S total was positive. And last but not least, we're going to look at Gibbs energy, or Gibbs free energy, which is a central concept in science. Okay, so we're back into our pack and we're looking now at page 15. And there's a little video link at the top here to one of my favourite videos looking at the drinking bird. So I do suggest you have a look at that. But we're going to be moving on today to look at equilibria and changes of state. So at equilibria, there's no overall change. So we say that we've reached what we call dynamic equilibria. And we're going to study this again when we study our equilibria topic. And we'll reintroduce the idea of Gibbs and entropy when we do that. But the important thing to remember here is that at equilibrium, our value of S reaches a maximum. But there's no change in S once we've reached equilibrium. Therefore, a requirement for equilibrium is that the change in the delta S total is zero. That's not to say that the entropy is zero. It isn't. It's usually at its maximum. But that the change in entropy, if we moved from that position, would be negative. So in this case, the delta S total must equal zero. So what does that mean in practice? Well, we're going to have a look at a bit of calculation. But just to remind ourselves of some of our very basic equations, we've got delta S total is system plus surroundings. System minus delta H over T, because remember that's our system surroundings term. And then we can use this little formula if we set delta S to 0 to work out the temperature at which a reaction becomes feasible. So we're looking at that bottom of that page, and we're going to look at basically water turning into ice. In other words, we're going to try and find the melting temperature of the water. So we've got here our little equation. We're going from solid water to liquid water. So this is where we started from, and this is where we're ending up. So expecting to see an increase in entropy as we go from the ordered solid to the more disordered liquid. So where we end up is 69.9. Take away where we started from, which was 47.99. Okay, and you get plus 21.9 joules per mole per Kelvin. And then I'm going to work out my system, and my delta S system is minus delta H over T. There's a bit of error there, the negative sign should be in there. Now, very kindly, they've given us the value for delta H already in joules per mole, so I don't need to convert it into kilojoules, sorry, from kilojoules into joules. So I'm going to go, that is 6012 divided by the temperature that we want. Okay, and we know, because of our little formula from earlier on, that must equal 21.9. So if we rearrange that, we get the melting temperature of water to be 274.5. And we all know that it should be 273 Kelvin, but with intolerances, that's not actually that bad. Okay, so now what we're going to do is we're going to turn the page over and we're going to have a go at some of the questions on the next couple of pages. So we're here calculating delta S total at different temperatures. Now it's very important to remember that if the system and the surroundings are both positive, then there is no temperature at which the reaction will not occur, because there's no way I could add those two positive numbers together and get anything other than a positive number. So we say it's feasible at all temperatures. Likewise, if both of those are negative values, then the reaction will never be feasible, no matter what the temperature is, because there's no way I can turn those into a positive number. What is the interesting ones is where one is positive and one is negative. So, for example, if I have a delta S system which is positive, but I have an endothermic reaction, well, I want my delta S surroundings term to be as small as possible. In other words, I want a very high temperature, because at high temperatures, system starts to dominate. And if system is positive, even though delta S surroundings are negative, as long as I've got the temperature high enough, I should be able to get it to work. And likewise, if I've got an exothermic reaction, in other words, my delta S surroundings is positive, if my delta S system is negative, as long as I keep the temperature low enough, it should work, because the surroundings term would dominate and it would outweigh the system's term. So there's things I can control with temperature to make my reaction flip between feasible and non-feasible. And that's an example I'm going to look at on this page. So what I'd like you to do now is to pause the video and have a go at calculating the decomposition of calcium carbonate and whether or not it's feasible at 300 degrees Kelvin and then at 1200 degrees Kelvin. Okay, hopefully you've had a time to pause the video, and we'll look at these calculations. We're going to start by calculating the delta S of the system. So delta S system is equal to where we end up, which was carbon dioxide and the solid calcium oxide. So I have 213.6 and 37.9. Take away where we started from, which was my calcium carbonate, 92.9. Now if I put those numbers into my calculator, I get plus 160.4 joules per mole per Kelvin. Again, I'm going to stop and just think to myself, does that make sense? Well, yes, it does, because I'm going from 1 mole of solid to 2 moles, including a mole of gas. So I'm expecting to see a positive entropy change here. If this time is negative, then I'd be a bit worried, because I think I've either done something wrong or my equation was wrong. Okay, so now I'm going to work out my delta H of reaction. Okay, and from that, my delta, using delta H reaction, I'm going to calculate my delta S surroundings. So my delta S surroundings is equal to minus delta H over T. So that's minus brackets. And this, because it's an endothermic reaction, I can tell that because it's got a positive sign. It's going to be 178. I'm going to remember to times it by 1,000 to turn it into joules. And the temperature I'm doing this at is 300 Kelvin. So I'm going to put all those values into my calculator, and I get a negative number, unsurprisingly. I get minus 593.3 joules per mole per Kelvin. Now I can calculate my total, because my total is just the system plus the surroundings. So that's plus 160.4, take away 593.3, and I get overall a negative number, minus 433 joules per mole per Kelvin when I do that answer to 3 sig figs. So no, this reaction is not feasible at 300 Kelvin. So no. Why? Because delta S total is negative, it's less than 0. So therefore it's not going to work. Okay. Now I can use the same numbers, or very similar numbers, to calculate what happens if I increase the temperature to 1200 degrees Kelvin. So I'm going to do that in this next section. Okay. So let's calculate delta S surroundings at 1200 degrees Kelvin. So my delta S surroundings is now equal to minus, again, 178 times by 1,000, but this time divided by 1,200. And at this temperature, I get a value of minus 148.3 joules per mole per Kelvin. Now, assuming that basically my delta H and my delta S system are unaffected by this increase in temperature. That's not 100% true, but I can kind of say it's this stage, again, it's relatively true. The calcium carbonate and the calcium solid, they're not going to be affected by this raise in temperature, and carbon dioxide is already gas anyway. So we're going to work out my delta S total. And that is now equal to my value from before, 160.4. this time minus 148.3, and I get plus 12.1 joules per mole per Kelvin. In other words, my reaction has suddenly become feasible. So therefore, feasible. And you've actually done this reaction. You might not have realized it, but you've actually done this one before. So this reaction you've come across before. You've seen it in your group 2 notes when we did the thermal decomposition of the carbonates. So when we did the thermal decomposition of the carbonates, you should have seen that they don't decompose until you heat them. That's because it's an endothermic reaction. But using these ideas, I could actually work out the temperature at which they should actually decompose. And as I said, you've seen that before in the videos. Right, what I'd like you to do now is pause the video and have a go at the calculations on the next couple of pages. So welcome back. I hope you've managed to have a go at those calculations. So we're just going to start at the top with the delta H of the reaction. So I've just drawn here a simple little Hess cycle, and I've used it to work out my delta H of reaction. So these are my elements along the bottom, and I'm using those to make these compounds or these compounds. So I've got my nice little cycle here. And I've worked out that it's a positive enthalpy change. So this is an endothermic reaction. I've calculated my delta S surroundings, okay, by using that number. So I've got my minus this value. I've remembered to times it by 1,000, so this value comes out as negative. I've then gone on and calculated my delta S system. Okay, so basically where I end up, take away where I started from, and this comes out with a nice big positive number, as I'm expecting, because I'm going from solids to a gas and a liquid, so I'm expecting that number to be positive. So last but not least, yes, I would expect this reaction to be feasible. Why? Because I've got an overall positive delta S total, and if that number is positive, it tells me the reaction is feasible. Hopefully you've had a go at the ones on the next page as well. So we just turn over. I've not done all the calculations here, but you should be able to work out you've got a system, which is negative, surroundings, which is positive, and the total, which again is positive. So it means the reaction is feasible. Okay, so that finishes just this little video for today. Tomorrow I'm going to upload a video looking at the 2 reactions. So if you want to get ready for that, you just need to have a look at the 2 reactions on the next page before we start chatting about them. And then we're going to move on to look at kinetic and thermodynamic stability, and then we're going to finish off the week by looking at Gibbs energy. Okay, well, stay safe, and I'll speak to you soon. Bye bye.